Okay, one is intrinsic. Intrinsic, why is it called intrinsic? Because we derived that it is an atom sitting in a crystal lattice is feeling a force, thermodynamic force, by which is given by negative chemical potential gradient. So minus del V del X, that is the chemical potential gradient, and so velocity is the proportionality constant we had mobility, and from there Cv will give you flux. From there we got and then we created it. So from there we got the diffusion coefficient under chemical gradient to be equal to mkT multiplied by the thermodynamic factor. Thermodynamic factor is given by 1 plus del ln gamma over del ln x. Thermodynamic factors for both components are same. And just without any chemical gradient, just the self diffusion or pressure diffusion coefficient equal to mk2. And pressure diffusion coefficient corresponds to a particular composition of the homogeneous alloy. So mobility corresponds to a particular composition of the homogeneous alloy. Thermodynamic factor also depends on the particular composition. Intrinsic diffusion coefficient depends on the particular composition. And we had intermixing term, that chemical diffusion coefficient or interdiffusion coefficient given by d theta, which is intermixing. So it is XA dB plus XB dA multiplied by the thermodynamic factor. And this dB dA is nothing but ds. So these are intrinsic. So we can write XA pressure diffusion coefficient plus XB pressure diffusion coefficient multiplied by the thermodynamic factor multiplied by this only there. Fine? This we already had talked about. And in the last class we derived what is V? Marker velocity. Marker velocity we got an expression like dA minus dB, dAc minus
by del x relax.
Or you can write in terms of pressure diffusion coefficient dA minus dB multiplied by F del XA del X. We had these two equations. We call them as Darken's equations. So that now note that this, what is V? So how marker velocity? So with respect to the Matano interface, you measure the velocity of the marker. What is marker? While at the beginning, when you butt weld two different homogeneous alloys or two different metals before annealing, so at the joint you put one wire or a foil of ceramic or of a metal of very high temperature which does not dissolve at the annealing temperature. So that moves because of this different diffusion coefficient of the component elements inside. So if you can measure the marker position with respect to the Matano interface, if you can measure the marker position at time t, and it is found experimentally that this marker position, say xm, marker position with respect to the Matano interface. So you have the Matano interface, that is your x equal to 0. From there, how much that marker position, that distance, that xm usually has been found to be varying with time, the diffusion annealing time, by this relation, which is a very characteristic of any diffusion process. So xm also has been found to vary with annealing time with the relationship of xm is proportional to root t. That means xm is constant root t. So xm, so dxm dt, which is v, xm dot equal to constant over root t, or we can write constant root t over t. Oh, there should be 1/2 also. So constant root t is nothing but xm. So velocity, so if you can measure xm after certain time of annealing, if you can measure the xm, that is the distance of the marker from the Matano interface, and you know the annealing time, you can find out the velocity. But that velocity will correspond to the where the marker is, what is the concentration of that. So this velocity corresponds to the particular composition of that.
Xm is the position of the marker.
Position of the marker with respect to the Matano interface. So at that position, whatever the composition is, corresponding to that you are getting a velocity. So this velocity is a function of composition again, like others. So from one set of marker, from a particular diffusional experiments, from one set of marker you will get V value for a particular composition. Although d tilde can be measured as a function of composition from using Boltzmann-Matano method, but V can be measured for a particular set of marker only for one value of composition where the marker is now. Okay, so these two equations which relate the experimentally measurable quantity d tilde and V, and these are, what are these? These are intrinsic diffusion coefficients. Intrinsic diffusion coefficients are kind of fundamental diffusion coefficients in any because we derived it from the perspective of what an atom is feeling a force of negative potential gradient, and from there we derive. That is your intrinsic diffusion coefficient. So this is the fundamental diffusion coefficient. So fundamental diffusion coefficient values are related to experimentally measured values. Okay, so these Durkheim's equations are like that way significant, and also if you and this DSC and DBC, DSC or DBC is nothing but tracer diffusion coefficient multiplied by the thermodynamic factor. This tracer diffusion coefficient also can be measured experimentally. If you know the thermodynamic factor, thermodynamics of the system very well, so these are also known. So it has other way also. One way is these are experimentally determined. You can determine experimentally, and you can relate the intrinsic diffusion coefficient with these two. And from two equations, two unknowns, you can find out DSC, DBC. That is one aspect of these Durkheim's equations. Another aspect is, if you can measure dA and dB, and if you have your thermodynamic factor variation with composition for the system, you can actually see that Durkheim's equations hold for many of the systems. Okay. So if you who was asking anyone?
So why is the 2D coming in the denominator?
Take derivative. Take derivative. Constant half root half t to the minus half. Now this, we talked about these thermodynamic factors. We are not, note that F for A and F for B equal, they are equal. How they are equal? From Gibbs-Duhem equation. What does Gibbs-Duhem equation say? At constant temperature and pressure, your summation xi mu d mu y equal to 0. Isn't it? At fixed temperature and pressure, xi d mu y is equal to 0. That is your Gibbs-Duhem equation, isn't it? And from there you just keep doing d mu a. You can replace it with d ln a. What I want everyone to do on your notebook, from this equation, can you show that thermodynamic factors are equal? Just do it on your notebook. So this is called Gibbs-Duhem equation. And your A, you can replace it with, you do it. And also note, if you come down few steps from here and note that dxa plus dxb equal to 0 should give fa equal to fb, means del ln gamma a over del ln xa should be equal to del ln gamma b equal over del ln gamma del ln xb. That relation you can get from the Gibbs-Duhem equation. If you just keep doing few steps, you will get to that step, that equality of the thermodynamic factor. Another graphical way of seeing it is if you have a Gibbs free energy curve, what is your x-axis? Composition. So, say gives free energy per atom leaves. Okay. Now, guys, what is this? Your A is here, your A B is here. What is this? Some fluctuation in the composition XB. Because of some fluctuation, say XB, your composition, if it comes here, then so because of some fluctuation delta XB, your mu B becomes so what is this length minus d mu A and this is or d mu B, and if you just parallelly make one line here, so this distance is nothing but minus d mu A. So from here you can see that this distance divided by this distance horizontally, that is if I take d mu A minus d mu A, that is your XB should be equal to this distance over this distance horizontally. And also you note that that is equal to this distance over the whole length. What is this distance? If you note, that is d mu, the whole distance is d mu B
minus d mu.
Also if you note, what is this distance? Mu B minus mu A. But after changing from here to here, this is the horizontal line. So from here to here, this is mu B dash minus mu A dash. After little variation in the composition, this is the difference in the chemical potential of the two components. Previously, this was the difference from here to here. So now this this length from here downwards, this length is, I am taking it to here. Instead of from here to, I am taking it here. Okay. So this total distance, I can take it from this to here. That is the mu B minus mu A, new mu B minus mu A. So new mu B minus mu A and previous mu B minus mu A is this one. So this is not change in mu b minus mu a. Everyone got this point? If you have not, I can repeat plus, but you have to say that you have not understood. You have not. Which point I missed it?
Is it the upper one 1 minus d mu a? The upper
See, what is this length?
mu b minus mu a.
From here to here, mu b minus mu a. So after changing of dxb from
Mu b dash minus mu a dash.
this to this, so this one is the mu b dash minus mu a dash. So mu b minus mu a. So this whole from here to here minus this much will give you change in mu b minus mu a. This is mu b minus mu a, previous mu b minus mu a. So I have to subtract this previous from the new mu b minus mu a. For that, what I am doing, I am just taking this one from here. This length is same as this length. Huh? I am drawing a horizontal line here, and I am taking this. I am making this parallel line like this. So this length is same as this length. So let me take that length to here. So from here to here means from here to here. So that is the new mu b minus mu a, and previous mu b minus mu a is this. So the difference is from here to here. That is the difference. So that will be change in mu b minus mu a. So that is change in mu b minus mu a, which was also is d mu b minus d mu a. But this length from here to here, this length divided by, so if you see the identical triangle, so that length divided by the whole length is nothing but
Slope.
same thing, like this length divided by the whole horizontal length is same as this length divided by this length from the identical triangle. The whole length is nothing but 1. So that's the equation I wrote. And also note that mu b minus mu a, what is this? The slope of the curve, del g del x.